So,
Yes,
so which mail ID do you check? The IIT KGP one or the Gmail one?
both I check. Both I
Oh,
check regularly. Why did you
okay.
send a mail and I did not respond for a long time?
Yeah, kind of.
Anything personal or?
No, sir, it was that I wanted to write the design docs using Markdown instead of plain text.
Right. I did not respond to that. I think I did. Yes, you can do that. Yes, of course.
Oh, thank you, sir. And
Ah,
yeah, I sent another one yesterday, but that's okay. That's about the singleton thing I was talking about.
you're deep.
Yes, sir.
Right. So I have read the mail. I'll respond. I mean, but regarding the design doc, yes, you can do that. That's your choice, and we are in the design space, so we will take liberty of doing different things. It's not necessary everybody has to follow the same system. Regarding the singleton, maybe I will add to the clarifications because it may be of value for others as well.
Yes, sir.
I mean, this is what happens when you work through a system. Lot of insights, lot of queries, lot of different ways of doing things come up, and you would like to keep on uh, keeping everyone in sync in terms of doing all that, because obviously
Yes,
maybe
sir.
it's not occurring to everyone. So it's a good learning exercise. I mean,
Yes, sir.
quite a few of the queries raised naturally tell me that, well, the specification could have been written better, but that's a life. Specifications are not written better. In fact, you will hardly get specifications so clearly written
This
in
good.
in
Yes.
in real life. But okay, so let's get started. Uh, mm, I have actually just now sent a mail through ERP with
Yes, sir.
two documents. So if you can just keep those documents with you, we'll in the next couple of maybe today I will just discuss a overview, but in the next week's classes we'll use it as a running example to illustrate different concepts and different UML diagrams through that, because obviously having a vehicular specification really helps. Okay, so let me get started now. Uh, Let me go to the presentation. Is the presentation visible?
No, sir.
No.
Sir, yeah, presentation is not visible. I think you have to again log in. You are not in the presenter section. You have gone to the invited section.
Oh my God. Oh my God. Here in my system, it is showing me as a presenter, but still I'll log out and log in again.
Yeah.
Is it visible now?
Yes, sir, it is.
Okay, okay, good. So, good morning, friends. We are back to the discussion on UML. So we will complete an overview of the diagrams and then go into some of the important specific diagrams. And for the purpose of illustration, I shall be using an example of a leave management system. Certainly, I cannot use the booking system as example here because you all would be actually doing the UML on that for that system. So I'll use a leave management system example, which we have used in earlier years. And I have sent the specification for the leave management system by mail just a couple of minutes ago. So please keep that handy. There are two PDFs in that. One is a plain one and another is a annotated one. So we'll discuss all that. So just to for a quick recap, we have talked about why we need a modeling language and the evolution that have gone through in the last about 3 decades in terms of UML, Unified Modeling Language. And this is kind of the hierarchy diagram in UML itself in terms of what different diagrams are. So UML broadly has two types of diagrams, the structured diagram and the behavior diagram. And there are different specializations of the structured diagram, importantly the class diagram, object diagram, package, composite structure, component, deployment, profile, and so on. So we'll focus primarily on the class and object diagrams more in our discussion. And there are finer specializations of these diagrams as well. On the other side, on the behavioral side, we have use case diagrams, activity diagram, state machine, and interaction. So, and specializations of those. And here too, we will focus on a few like use case, activity, state machine, sequence, and so on. So, as you can see, the two broad categories are structure and behavior, which is, as you can understand, irrespective of what system you are building, there is a static structure of the system. And this static structure could be at different levels of granularity. And that is the reason you have different diagrams for them. And the behavioral diagrams show the dynamic behavior of the objects in the system as time progresses. What are the kind of changes that you expect? What are the kind of actions? What are the actors? And what are the activities that happen are expressed in behavioral diagram. And as we understood that abstraction at every level is very important, and abstraction is what talks about one primary aspect while mostly ignoring the other details so that it remains humanly comprehensible and clear. So that is the reason you just do not have just two, conceptually it is just two diagrams, structural, how the structure of the system is and how does it behave over time. But we specialize into various kinds of diagrams in each one of these categories because we want in every diagram, we focus on certain specific aspect and ignore the rest. And obviously, we show the interrelationships. Now, getting deeper, if we look at the right-hand side, the behavioral diagram, then the first and the foremost important is the use case diagrams, which represents the requirements of a system, including internal and external influences. So this diagram is used to capture the user specification for a system to be built. Very simple concept of use case is how would you want to use a particular system, right? So it is if you are kind of making a wish, you are kind of dreaming about the system, and if you take the whole system as a black box, then who are the people who will interact with this system? What are the kind of inputs they are expected to give? What are the kind of outputs that are expected from the system? And even internally, if there are actors who will need to, manage the system in some way, and what are the things that they will do. So use case diagrams, as a term, use case is how you use. It's a case of how you use. So you are, if you look at your booking system, then certainly one use case is very clear, that you will have to make booking. Making booking is a clear use case, right, where you have an external actor who could be the person booking, because now you have online booking, so people book themselves. Or it could be the counter, the executive at the counter, who is doing the booking for someone, and she will interact with the system, with the booking system, by placing the booking order, and the system will respond in terms of confirming the booking, or in terms of saying that the data is not valid, or in generality it could say that the booking request is valid, but the availability is not there, and so on. There could be other use cases internally also. There will be a system administrator who is looking into the system from inside, and keeping track of all the bookings, actually generating internal reports for each and every train that has to, the reservation chart for the train. These are not given in your assignment, because we did not go to that depth. But in an actual system, there'll be use cases to create reservation chart for a train. There'll be a requirement to identify what are the berths that are available for further booking, and so on. So use case, I mean, we always say that if we are doing a system, then what is the use case? Who will use, for what purpose, and how? Use case diagram try to explain that through a means of certain very basic icons. So that's the starting point. Activity diagram models the flow from one activity to another activity. The activity can be described as an operation of the system. So it helps to capture the system's behavior in the context of activities. For example, you have set a booking request. So what is the first activity? First activity is to input passenger details. It is required to input the details of the booking itself, which is the travel date, say booking class. There may be booking categories, and so on. So that's the first activity. That has to follow internally in terms of variety of data validation. You have to make sure that the passenger data is a valid one. Like the passenger has a date of birth, which is a valid date, which is not in future, has a travel date, which is in future, which is not in past, and so on and so forth. And then once that validation is done, the next activity would be to, in a real system I'm talking of, would be to check whether the requested reservation is available. In your example, we are assuming infinite capacity. So, but in reality, the next activity would be to check for availability. And if it is available, then generate the booking. There could be, again, your system is ignoring that. There would be then the activity to generate payment invoice and actually do the payment. Once that is done, the booking is confirmed, that's printed out, or it's given out as a mail. And that's one part of use case, which is booking is broken. That use case will have several such activities, and it could be at a different granularity level. The third is a state chart diagram, which is used to describe different states of an object during its lifetime. So state chart diagram is kind of, just to understand at the first level, you could take as a kind of generalization of state machine. In a state machine, what we do is we have states and we have transitions. States get input, And based on that input, it makes a transition from one state to another. Right? That transition could be to a valid state, it could be to an invalid state, and so on. But every state itself is otherwise passive. It just can take a input and make transition. It cannot do anything else. But in a state chart diagram, you generalize this. For example, in a state chart diagram, a node itself could be a state machine, that it does a certain set of things, and you can think of that the whole state machine, say if you say it's an FSM, finite state machine, then it what does it do? It takes the input and finally gives you an output. So, and based on that output, you decide on what you will do next, right? So you give an input for a booking, and you get an output of invalid data or valid data, but booking not available, or booking has been done. So based on these inputs, the system go to a different state, right? So you are kind of making a higher level abstraction of in terms of the state machines, where every node is kind of not a passive one, but could by itself be an active component, right? So and this can recursively build up. So that's kind of things are called state chart diagrams. We will talk a little bit more later on. Some of the other diagrams, like behavioral diagram, is in the behavioral diagram is in terms of interaction. Most important in that is the sequence diagram, which basically try to set the ordering of different messages that go in the system. So one of the key ways to look at UML models or in system in general with strong object orientation is to think in terms of a client server model. So we say that every object is one who can accept a message as a request for service. So what do we know? We know objects have states and objects have behavior, right? So behavior is what is the interface. So an interface, so when you call an interface, you can think about this as you are sending a message to that object. So based on that message, the object will react and give you a response, right? So that these are the events that happen in terms of a client server system, and you can think about the whole design in terms of as if a pool of objects are floating around in the system at any point of time, and each and different objects are sending requests, messages to other objects, and they are responding through messages again, and based on that again you send out messages. So this messaging system in the client server kind of a structure is what the sequence diagram tries to capture as to what is the first message that has to happen, and based on that who will get that message, based on that what is the expected output. There could be conditional output also, like you give the booking data, it could be valid, it could be invalid. So in each cases, what is the object which will get the next message, and so on. So it tries to talk about the logical ordering of these messages. So you can see that compared to activity diagram, this interaction, that's why it is called interaction. What is interacting? The different objects of the system are interacting. So this is little bit at a more granular level, where in activities you are talking about a broad activity. Okay, I have to validate the data. But here you are talking about invalidation of the data. What are the objects involved? And naturally, there could be 10 different validations. What is the order in which I proceed? For example, I'm trying to validate the passenger data, and I have a date of birth. Naturally, the first validation is to see that it is a valid date of birth. If it is a valid date of birth, then you have to see whether the date of birth is in the past. It cannot be in the future, right? Now, if the date itself is an invalid date. You have given 29th February 2021. That's an invalid date. Or you have given it in a wrong format or anything. Then naturally the next validation of whether it is in past or in future does not arise, because you cannot do that. So this is this is all modeled through sequencing of messages that flow around in the system, right? So that is what is captured by the sequence diagram. Now, communication diagram, we say that sequence diagram is a temporal ordering. I mean, in terms of time, how the messages are getting exchanged, whereas communication diagram is a spatial ordering of the messages, where you try to capture the different objects and the order in which they interact between them. You are not looking at the sequencing of them, but you are looking at from the objects. Now in sequence diagram, you primarily look at the messages. They happen in a temporal order, so you see which message, then what message, then associated with that is the object. So your primary focus, your aspect of sequence diagram are the messages, whereas the aspect of communication diagram are the objects. You look at, these are the pool of the objects. This object can send this message to that object. That object can send another message to a third object, and so on. You are not looking at the sequencing of messages there. Rather, you are looking at what are the objects and how they can interact through messages here. So that makes it the communication diagram. Then you have the timing diagram, which captures the state of an element and how it changes. So one significant difference from sequence diagram, two significant difference I'll say from sequence diagram, because these are all similar interactions. One is in sequence diagram, you are just focusing on the messages and the order in which they occur. In the timing diagram, you are focusing on the change of change of states that happen to elements. I mean, because once you send message, the state of the object is changing, and how those changes happen over time. That is, so you are trying to look at more in terms of the internal state change of the objects, and most importantly, it may have real-time constraints. So systems which are more sensitive to real-time issues will have stronger timing diagram. Now you will argue that everything is real time, because finally you are working in the real world. So for example, if in a booking system is real time, you don't expect that you give an input for booking and then the response come after 1 hour, right? But we talk about a system being real time when a typical response time of a system is kind of comparable, or without a good design, maybe more than the expected real time. So if you give a booking request to a system, the expected response time would be how much? 30 seconds, or maybe you would accept a minute also. And a typical system time required for doing this may be in the order of milliseconds, right? So you can see that it has a real time, but the real time is not a major concern for your design. So you will have more focus on the sequence and communication diagram than the timing diagram. Whereas if you are making a system, say a computing board for A to D conversion, analog to digital conversion, let's say, right? So analog to digital conversion are complex systems which are often built. Now in that, you have very strict timing requirements from every state to the next state of the system, because otherwise you cannot meet the real-time requirement of being able to do this as the at the frequency of the signal, which is very, very high, and you want higher and higher frequency of signals. So you are doing this A to D conversion for signals which may go go at the level of gigahertz. So your response time expectation is nanosecond, and maybe your system actually also has a response time which is in nanosecond. So unless you design the timing with proper real-time constraints, your design may not come out very well. And timing diagram try to focus on those kind of aspects. So you'll see very little use of that in terms of the booking system example, but in other systems that will be required. Interaction overview diagram is more in terms of certain little bit more higher order interaction flow consisting of various sequence, collaboration, and activity flow. So interaction diagram does not get to the depth of messages or objects or states. They look at, okay, if I have a typical flow, what will be a typical flow? So kind of you can say that different happy paths, different exceptional paths could be modeled in terms of an interaction overview. Again, I mean, the kind of systems we are talking of, interaction overview diagram will have less use, but these are required in several other systems. So these 7, so we have talked about broadly. If I go back to slide 10, so we have talked about broadly this use case, activity, state machine or state chart, and these interaction diagrams, broadly these 7, and of which we will focus in more detail in terms of use case, activity, state machine, sequence, and communication primarily. So now let's shift our focus somewhat to the structural diagrams. I'm on slide number 14, module 21 here. So the most important structural diagram, which kind of you already know, except for the UML syntax and semantics of expressing it, are which model the analysis and design of the static view of an application. So what class diagram tries to do is to capture the key abstractions of the system at the first level. Right. So kind of when we take up the assignment 3, we see that there are classes already identified. So those are the key abstractions. For example, station is a key abstraction. Railway is a key abstraction. Booking class is a key abstraction. Your booking itself is a key abstraction. Passenger is a key abstraction. So these are the key concepts in the system. And you will, at the first level, make a class diagram involving each one of these concepts being represented by a class or by its specialization. Pretty much the way we write the code, but it is written in a language independent manner. But the second part, please keep this in mind, is later refined and with details of every abstraction for reference. So you say a booking class is my key abstraction, and then you say, well, it has to be refined in terms of having a variety of booking classes. There could be a first class, there could be AC3 tier, there could be AC2 tier, and so on and so forth. So how will that refinement work in terms of the abstraction? And then this key abstraction of booking class is getting more and more specialized. Now, you can take a kind of a hierarchical view of doing this. You could say that, okay, I will classify this abstraction of booking class in terms of whether it is whether it has bath that you can lie down, or it has only seats, that is, it's just a seating. And we will have 2 abstractions of classes involving sleeping, the classes involving sitting only. And then we'll say, okay, AC3 tier is in the sleeping category, AC chair car is in the sitting category, and so on. And then we may have further refinements of these abstractions. An alternate view could be, okay, finally, I mean, that some of you have also expressed, that I will refine it given the fact that I analyze that the key abstraction of booking class is necessarily at the end a set of attributes which differ between different booking classes. So why not I'll just do one flat hierarchy level and do with that. I could do an orthogonal design also. I could say that, well, I have a booking class which represents a concept, and it has a set of values that it takes. It is not, it is governed, it is constant, it's not expected to change, but it has every different collection of values actually represent a different concept, but they are completely interrelated because they have the same structure, they have the same representation, they have the same kind of use. So we talk about whether it's a sitting or sleeper, whether it is AC or not AC, whether it is luxury or not luxury, and so on and so forth. So I can do an orthogonal design using parametric polymorphism also. I say, okay, this is because I need the same information, it's just that they are of different types. So which suits very well in terms of the parametric abstraction. So these are all refinements. So in your assignment 3, you are trying to do the refinement in terms of a hierarchy. In assignment 4, we will see that we will ask that you can have an orthogonal design. You can do a parametric abstraction in these cases. Further refinements may actually identify more abstractions. For example, say, you will not say that, say gender is a key abstraction, right? Because it's incidental. But as you go in the refinement, you see, okay, gender is also a concept, right, which can take 2 possible values, right? So I can identify that at a later point as an abstraction, and I can represent that as a class, which is again, has 2 specializations in terms of having more refined concepts. So as you go through refinements, the class diagram will model the static view of an application to more and more and more detail till it comes to a point where it becomes easy to take it to a vehicular language, whether it is C++, whether it's Python, whether it's Java, whatever. The other structural diagram, which is very important, which are object diagrams, which represent an instance of the class diagram. So in the class diagram, you see a lot of attributes. You have a set of interfaces, but it does not tell you that at different points of time, when you instantiate a class as an object, how does these attributes really look like? At a particular moment, what will be the state of the object? What will be the kind of attributes which must remain populated? What will be the attributes which may change? What will be the attributes which are primary? That is, they need input for the construction time. What are the attributes which are secondary? An object view gives you these kind of snapshots. So that's the object diagram. Package diagram is again something which is relevant for more complex systems, not like just a booking one, it becomes only one package. So wherein you try to encapsulate the major components of the system, right? So if you think about your laptop or your PC, and you try to model it in UML, you will easily identify number of packages. You have a package called CPU, you have a package called memory, you have a package called keyboard, you have a package called network interface, and so on and so forth. So these are subsystems which are built as a complete system, packaged inside, so you make it a black box at the end, living with only just the interfaces, and then you integrate these packages together to build the whole system. And so you have the different dependencies that these packages may have. If two packages have a lot of dependency, then you have to reconsider whether they are truly separable packages, or they should be put together, and so on. Right? So these are the structural diagram views that you have. Then you have a set of structural diagrams for composite structure, part, subpart, and interfaces. You have component diagrams, which is relevant if you have the physical system, and how to implement it in terms of the physical system, so that it can go down to the level of servers, active components, IoTs. Many of the systems today have variety of IoT, Internet of Things. You can have IIoT, Industrial Internet of Things. You can have MIoT, Mobile Internet of Things, and so on. So these are physical components, which physical aspects of the system where you need to put your different packages. So you can have component diagram, more important for the implementation side. You have deployment diagram, which describes the hardware components and software components and how are they deployed. I mean, how many physically, finally, at the end of the day, how many physical servers you will have, which software component will run on which server. A particular server may run multiple software components. One particular software component may be huge enough or may require turnaround which is very steep, so that it might run on multiple servers in parallel, and so on and so forth. So kind of it is used to capture the hardware topology, architecture of the system. Then you have profile diagram, which is defined to define custom stereotypes, tagged values, constraints. So these are certain ways to really describe a meta model of your platform, and so on. So as you can see that these this later part of structural diagrams are going more towards the implementation side. And I mean, we will not get into the details of that because we will not have that much of time. But this is good to know that what exists where. Okay, so having said that, let me just move on to, I've gone to the next module, and SDLC, So what I want to now talk of is, on one side, we have the SDLC, Software Development Lifecycle Processes, right? And we are talking about a variety of diagrams. So what we want to characterize is which, given a phase of SDLC, what are the diagrams that are relevant? Or the other question as well, given a diagram, what are the phases that it impact? Now, naturally, we have discussed a variety of SDLC phases. But I have just taken the simple linear, waterfall kind of a model to explain here, because if you look deeply, whether you are doing waterfall, whether you are doing iterative incremental, or you are doing spiral, or you are doing agile, whatever you are doing, these are the tasks that you have to do. The order in which or not the order, but the extent to which you do them differ from one SDLC model to another, but these are the tasks, right? So it for our discussion, we'll take them as a linear one, but with the iterative feedback. So these are the stages that we have talked of, and these back arrows are the refinements. So you do a requirement specification, you get an analysis, get to the analysis, and then while doing the analysis, you might need to go back to requirement specification and make changes to what requirements you have captured, and come back to analysis again, and then go through this loop till you stabilize, come to a fixed point in the analysis, and then we go over to design, where while doing the design, you might need to go back to analysis and keep on doing in this loop. It might happen that you find something in the design so that you have to go back to analysis and you analyze and see that, okay, you'll have to again go back to the captured requirements and start making changes from there. So it can go through this kind of loops conceptually. We are not talking about the execution. In SDLC models, we actually talked about the execution of it. Here we are talking about conceptually what needs to be done. So given this view of SDLC, if we look at what kind of role object-oriented system and design play, then we will see that primary of object-oriented style impacts the first three stages: requirement specification, analysis, and design. That's where you bring it to a well-designed object system. And then you get into system implementation using OOP, because once your design is complete, you have an object-oriented system. Now you have to make sure that you maintain it. Like you can make an object-based design and then implement it in a way so that you break all, you make everything public and you break all encapsulations, or put everything as flat and so on. So you have to maintain that. So it has to go through that implementation. Test itself has to be object oriented. We have talked about, say, unit tests for that matter. So which clubs directly with the objects or classes that we have talked of. So these are the typical views that you'll have. Now, starting with the requirements phase, so we'll primarily talk about the initial. Talking about the requirement phase, there are, in the requirement specification phase, there are three possible activities, three possible models. One is constructing the use case model, constructing the problem domain model, and constructing the interface model, right? So these are conceptually, and this the way you see this diagram is actually again in UML. So you'll understand this. So this kind of shows the way you are doing the activity. You can start here, do any of these. These are the outputs, like the white boxes are the outputs that you produce. And once you have completed all of them, this bar basically, so this kind of started as a very old model called PetriNet models. If you're when you have studied your, say, communicating sequential processes in OS and other areas, then you'll see use of these kind of models there as well. So it says that this is where your activity starts, and these are the possible paths you can take. And only when you have completed all of them, then you make an assessment that whether you need to revisit. If you need to revisit, then you go back and do these again. Otherwise, there's no further use case, and you go ahead. So now, so what are these three aspects? One is a use case model we have talked of. That is, we are identifying what the user wants to do with the system, right? Who wants to do, what needs to be done, how it should be done. Use case model. So that will generate a use case model. Then what you need to do is, from that wish, you need to make a problem domain model. That you need to model the domain in which you are working in terms of abstractions. So you need to, from the booking, you need to identify that in your domain of booking, there are key entities like the station, the railways, the booking class, the passenger, and so on. And the third is constructing the interface model. How will you interact with the system? So it often goes down to doing variety of user interfaces. Earlier we used to say text-based input and GUI. Now, of course, you have so many different ways to do a user interface. It could be a voice-activated user interface. You could do a text activate. I mean, text. Of course, you can do traditional GUI. You can do more advanced GUI and so on and so forth. For example, I want to do a I want to book in the system, and in terms of passenger data, I would not like to put on all those details of what is my name, what is my date of birth, what is my Aadhaar card number, what is my gender, and so on. But I want an interface where I'll just show my face, and the system extracts all that data. So it could be a very different kind of interface that can happen. So in the requirements phase, therefore, coming down to specific models. So this diagram again is an UML diagram. So which says that the requirements model, if I have a concept called requirements model, the models required at the requirement specification phase, requirement models have three components: use case model, problem domain model, and interface model. And these numbers by the side of this line indicate how many instances of the model I might have. And these diamonds are not filled up. So there is a semantic difference between having a open diamond and a closed diamond, or a white diamond and a black diamond. We'll talk about those, but this necessarily is component. I mean, you can, to the extent that you have done so far, you can take this as a component specification. The requirements model has a use case model, has a problem domain model, and has a interface model. Use case model, in turn, has a component which is the use case diagram, which is a picture. Okay? So it has one of that. But it will also have description of use cases, because understand that use case is the first level where you're transforming a natural language description into a structured model. So at the first step itself, you may not be able to capture everything exactly correctly, and different behavioral requirements will have to be still captured in short, more crisp natural language description cases. So you can have, so you will have one diagram, but you have a star here, which means zero or any, the typical clean annotation. So description of use cases. So you can have multiple of them, and these two together make your use case model. Then in terms of problem domain model, you have the UML class diagram. Right? You'll have only one class diagram. Obviously, that is what will capture everything. And in terms of interface model, you may have multiple UI specification. Could be text, GUI, both, or even in text, it could be multiple of that. And you will have associated specification of system interfaces. You do not have yet in UML, you do not have diagrams for user interfaces or user interface specification. So the interface model will talk still in terms of somewhat non-standardized, unstructured manner to some extent. So this is about the requirements phase models. Moving on to the next analysis phase. So this black dot on top tells you that you are coming from, if I may go back, slide 7. Here you ended with this black circle. This kind of FSM notation. This is the end of this diagram. Similarly, on slide 9, in the analysis phase, you have, this is the starting. So you already have those models, remember. So now in analysis, what you primarily work on is refine the problem domain model. You say, okay, this is a problem domain model we have got, and this is what I see. This class has to be a singleton. This class needs specializations and so on. And you also start constructing the behavioral model. So you have on one side the structure model, which is already constructed from top. You are refining that. And you have to start building the behavioral model. So what the behavioral model that gets constructed, it is then again the similar kind of loop of refinements will keep on happening till you have come to a point where no additional requirements are necessary. So looking in terms of the UML diagram, the analysis phase will have analysis models which consist of has a structure model, has a behavioral model. Structure model is the class diagram, and behavioral model is 0 or more of sequence diagram, collaboration diagram, state chat diagram, activity diagram. You may have all of them. You may have multiple of some diagram. You may have none of them, and so on. It depends on the requirements, but this is together is your analysis model, which so wherein you'll have all these different UML diagrams giving a complete analysis of the system, validated to your level of analysis given the requirements that you had. And you move on to the design phase where you now with this model you start working on the system design and first create the high level design model, then go into doing the detailed design and create the low level design model, right, and iterate over that. So in terms of the design model, you have the structure model, you have the behavioral model. These are already built, and you will have can you see the presentation?
Yes.
Yes, sir.
So I think we were here when I lost. So in terms of the design phase, you have design models. So you have component diagram and deployment diagram, which comes from UML. But typically you have architectural description as well, which is still under development in UML. So it is still kind of a non-standardized one. And you have the other structural and behavioral models that we have already discussed. So that is how your design model works out. Finally, in the phases of system implementation, like the remaining phases of SDLC, will implement the models that we have built so far, and some of the additional diagrams will be used here. We will not go into that much of depth. We are just trying to gather a basic understanding of UML. So this is what from the next class, we will try to take this example of leave management system, part of the booking system, not much, because I want you to do that exercise on the booking system, and discuss about these UML models, which we have listed for requirements phase, for the analysis phase, and for the design phase. Okay? So if there is any quick question, I can take that. No questions? Okay. Thank you then. Have a nice day and a good weekend. We meet again on next Wednesday. Thank you. Bye.